Good morning everyone. Today me and my teammate will discuss about exascale computing and advanced parallel computing models. Our next slide is content. Here is our content. Let's move on to the introduction of our presentation. What is exascale computing? Exascale computing is performing operations such as calculations with high resources. HPC, known as high performance computing, falls under exascale computing. For example, let's say we need to calculate the weather detail to see if tomorrow is rainy or sunny. Calculating via a single computer takes a lot of time, sometimes that we don't have. In HPC concept, many computers act as one to complete complex calculations like calculating weather details as fast as they can. So, in HPC, we connect resources together to create a more powerful machine. The resources connected are CPUs, GPUs, and memories. Let's move on to our next topic, which is importance of exascale computing. Our first subtopic is accurate research result. With exascale computing, we can achieve more accurate research results. HPC helps to achieve this. When we point enough resources to a complex matter, we can achieve the results more accurately and fast. Our next subtopic is advancement in AI and machine learning. Exascale computing speeds up the AI models and improves decision making. Our last subtopic is security advancement in countries. Most countries use exascale computing for security purposes, such as defense simulation and cybersecurity, by helping them stay ahead of enemies. Let's move on to our next topic, which is overview and of exascale computing. Exascale computing is a high-performance computing framework which can perform no less than an exaflop, which is 10 to the power 18 floating point operations per second. For this reason, the system is capable of performing quintillion calculations within 1 second, making it 1,000 systems faster. Our next topic is history and milestones. Terascale era. In 1997, a computer system was built by Intel which was installed at Sandia National Laboratories was the first system that broke over teraflop limitation by achieving a goal of 1.8 teraflops. Our next subtopic is petascale era in late 2000s. In 2008, a system broke the petaflop barrier. The system was installed at Los Alamos National Laboratories which was created by IBM. Roadrunner was the name of the system. The target it achieved was 1.026 petaflops, which means 1 quadrillion flops per second. Our next subtopic is exascale initiatives from 2010s to present. The United States of America started to develop exascale computing in 2011 with the help of Department of Energy, and China started the development in 2012, giving the competition to the market. However, the US is leading in exascale computing at the present. Pre-exascale systems. In the year 2018, Japan and the European Union launched supercomputers, but they were not identified as exascale computers because they did not achieve the rate of minimum calculation. For a system to be called as HPC, known as high performance computing, it needs to achieve the minimum rate of exaflop rate of calculations. However, it was halfway through. Japan's Fugaku supercomputer achieved zero point 0.5 exaflops. Our next topic is architect and system design. There are two topics under that topic, which is processor architect and node architect. In exascale computing, the developers focus on power efficiency and the ability to balance complex workloads like simulation and calculations. Below are the key characteristics of architect and system design of exascale computing. High core count. The processors used in exascale computing features high core count, which means that these processors have a large number of cores built in them. Processors need to be energy efficient. To accomplish this, techniques such as low power modes and process optimizations help. Let's talk about node architect. Nodes are fundamental building blocks of an exascale system. A node typically consists of multiple processors, both CPUs and GPUs, memories, and network interfaces. Exascale node architectures are designed for extreme scalability and parallelism. Multiple processors. Every single node has several processors, both CPUs and GPUs. The mix of CPUs and GPUs allows for high flexibility and performance over a variety of complex workloads. Shared and distributed memory. In high performance computing, HPC, nodes usually have a shared memory architecture where multiple processors access the same memory, often using DDR4 or DDR5. This allows processors within the same node to easily share data. I'm going to invite my teammate Omidu Kumar to go with our presentation from now on. Omidu?
Thank you, Kishan. Exascale computing or high-performance computing refers to systems that can perform a quintillion calculations per second. These systems are changing the way industries operate by enabling faster and more complex calculations. We will cover how exascale computing is applied in weather forecasting, finance, engineering, and medicine. Weather forecasting is one of the areas where exascale computing is very important. Predicting the weather requires analyzing large amount of data such as wind patterns and temperatures. HPC systems allow meteorologists to run complex models and provide accurate forecasts over several days. Climate modeling also relies on HPC, as it helps scientists study long-term climate changes and predict future environmental conditions. However, setting up these systems is expensive, and not all regions have equal access to this technology. This limits the ability to predict and respond to climate issues globally. In the financial sector, HPEC is used to run complex models that helps companies understand the risk caused by economic changes, market shifts, and investments. HPC allows quick analysis of financial data, enabling traders and analysts to make informed decisions faster. It is also useful for detecting fraud by analyzing large amount of financial transactions and spotting unusual patterns. However, the high cost of these systems create a gap between larger and smaller financial institutions, making it harder for smaller firms to keep up with the latest technology. HPC is crucial in designing and testing vehicles and aircraft. Engineers use exascale computing to simulate how materials and structures will behave under different conditions, such as stress in cars or airflow around airplanes. These simulations help improve designs, reduce production costs, and increase safety. HPC also speeds up product development by replacing physical prototypes with virtual simulations, which allows companies to bring new product to market more quickly. However, the high cost of HPC systems can be a barrier for smaller companies, limiting their ability to compete with larger firms. Exascale computing is opening new possibilities in medicine, particularly in drug discovery and biological modeling. With its ability to perform a quintillion calculations per second, HPC allows researchers to simulate biological processes on a large scale, offering insights into diseases and enabling the discovery of personalized treatments. While exascale computing can speed up drug discovery by testing thousands of compounds simultaneously, as we saw during the COVID-19 pandemic, it raises questions about whether it can fully replace traditional methods like clinical trials. Despite its speed and power, real-world clinical trials and regulatory approvals are still necessary, creating debate about the future role of HPC in medicine. One of the biggest challenges in medical diagnostics is the lack of high-quality label datasets, especially in areas like cancer detection. Due to privacy concerns and the need for expert labeling, it is hard to find large, diverse datasets. The Typhon framework helps address this problem by using HPC to train machine learning models on multiple datasets at the same time. In cancer detection, for example, Typhon trains models on different types of medical imaging, such as MRI, CT scans, improving diagnostic accuracy. However, despite these advancements, implementing these models in the real world medical settings remain challenging. Medical professionals are often concerned about the black box nature of AI, and many hospitals lack the necessary infrastructure to use these models. Exascale computing has the potential to integrate various types of medical data, from electronic health records to genomic sequences, into one model for personalized healthcare. This approach allows for the creation of detailed patient profiles that take into account genetic, environmental, and lifestyle factors, leading to highly tailored treatments. However, integrating such diverse data raises concerns about privacy and security, especially in healthcare, where patient confidentiality is crucial. Additionally, the fragmented healthcare system makes it difficult to merge data from different sources. Until these challenges of data compatibility and privacy are addressed, the full benefits of exascale computing in healthcare will not be realized. While HPC provides many advantages, it also has significant limitations, such as cost, scalability, data management, and programming. HPC systems come with significant costs, which can be divided into several categories. First, there is the hardware cost. HPC systems rely on advanced processors, GPU, and specialized accelerators like FPGAs. These components are much more expensive than standard hardware because of their sophisticated architecture and enormous processing power. Additionally, HPC requires vast and fast storage systems to handle the large datasets generated during computations. Furthermore, high-speed networking solutions such as InfiniBand are necessary for efficient data exchange between nodes, but they come with a high price tag due to their low latency and high bandwidth capabilities. Next, there are software costs. Many HPC applications and operating systems like Red Hat Enterprise Linux require licensing fees. Software tools used for simulation and analysis, such as MATLAB or ANSYS, can be costly, especially when scaled across thousands of processing cores. Specialized middleware and development frameworks also come with proprietary licenses, adding to the overall cost. Operational costs are another major factor. Energy consumption is a significant expense, as large HPC systems can consume several megawatts of power, costing millions of dollars annually. Additionally, advanced cooling systems such as liquid cooling or immersion cooling are necessary to manage the heat generated by these systems, further increasing both initial setup and ongoing operational costs. Finally, there are human resource costs. Managing and maintaining HPC systems require highly qualified personnel, including system administrators, data scientists, and software developers. The need for such specialized skills lead to higher labor costs, making it difficult for smaller organizations to afford the expertise required to operate these systems efficiently. Physical space requirements are a key concern. HPC installations require large data center spaces, and expanding these facilities can be difficult and expensive. These spaces need to be equipped with the necessary power and supply and cooling infrastructure to support the HPC systems. Building or leasing such as data centers with the appropriate structural and electrical infrastructure is a significant investment. Moreover, scalability limitations often arise. Simply adding more processors or nodes to an HPC system that does not always result in a linear increase in performance. This is due to factors like communication overhead between nodes, data dependencies, and limitations in memory bandwidth. These issues can reduce the efficiency of scaling HPC systems. Additionally, not all algorithms and applications scale effectively across thousands of processors. Optimizing software to take advantage of thousands or even tens of thousands of processing cores is a difficult task. Without proper optimization, the benefits of adding more computational resources are limited, making scalability a significant challenge for both software and hardware. Managing the large volumes of data generated by HPC applications presents several challenges. HPC applications, such as simulations or big data analytics, produce massive amount of data that require specialized storage systems. These storage solutions need to be fast and capable of handling the high throughput demands of HPC workloads, which often means using advanced hardware such as SSD arrays and specialized parallel file systems like cluster or GPFS. This level of storage comes at a high cost and adds to the complexity of the infrastructure. Another issue is data transfer and accessibility. Transferring large datasets between storage and compute nodes can create bottlenecks in the system, slowing down processing times. Efficient data management and access methods are critical to avoid delays and optimize performance. In addition to storage challenges, ensuring data integrity, replication, and redundancy is essential for maintaining reliable HPC systems. This process adds further complexity and cost to data management. Moreover, analyzing and visualizing these large datasets requires specialized tools such as MATLAB, Python libraries, and other complex analysis software. The process of cleaning and pre-processing the data before analysis is often time-consuming and requires significant computational resources. Programming for HPC systems comes with its own set of difficulties, mainly due to the complexity of parallel programming. Writing efficient parallel code is challenging because developers must account for issues like data dependencies, where one task cannot process until another is completed, as well as race conditions and load balancing, which can slow down the overall performance of the system. Parallel programming also demands a deep understanding of how different processors work together. HPC systems often include a mix of CPUs, DPUs, and other accelerators like FPGAs. Developing software that can efficiently utilize these diverse hardware components is a complex task, and many programmers need extensive knowledge of parallel algorithms and architecture to do so. Even after parallel code is written, optimizing it for maximum performance is another major challenge. This requires fine-tuning memory access patterns, minimizing communication between nodes, and efficiently utilizing cache hierarchies to avoid bottlenecks. Specialized tools like Intel VTune and NVIDIA Insight are often used for profiling and optimizing HPC applications, but using these tools effectively requires significant enterprise. Furthermore, HPC applications rely on various libraries and frameworks. Ensuring compatibility between different software components can be difficult, and maintaining and updating these applications over time is resource intensive. Debugging and testing parallel applications is also far more complex than traditional programming due to the concurrent execution of multiple sets of processes. Ensuring correctness and performing across different scenarios and hardware applications takes considerable time and effort. I hope now you have an idea about exascale computers. Thank you for listening.